All right, everybody. Welcome to week 2 of lecture. This week is going to be on mineral weathering and soil solution chemistry. So just remember back to last week's lecture and that soils are about 50% solids. That's 45% mineral matter, 5% organic matter, and about 50% space. So that's about 25% pores, which is filled with air and gases, and 25% liquid. So when all those things start to get together, they go through a process called weathering. Now, weathering, you'll remember, has a couple different things that happen. So first off, weathering starts to break down that mineral piece here into smaller and smaller particles. Now, when those particles get smaller and smaller, the total surface area of the mineral surfaces increases. And so you'll see that the kind of perimeter of this is getting bigger as you get more and more mineral particles. So weathering can happen by two different processes. The first type of weathering is called physical weathering. So physical weathering is when the rocks are physically broken apart. And that can happen a couple different ways. Here we see two pictures of examples. First one is, you can see it's like a root or something like that. It's a biological agent. And you see the tree starts to grow in here. And as it grows, it expands out and out, adding those tree rings. And eventually it just puts so much pressure on the rock that the rock will crack. You can see that it's a pretty clean crack right here. Another way that rocks can physically weather is from water. So water will get into a crack in the rock and then it will freeze and it expands, right? When water freezes, it expands. And then similarly, the rock just cracks. And you can see how here you get these very clean breaks as the rock cracks. Another example of weathering, a different type of it, is chemical weathering. So chemical weathering can happen a couple different ways. So here is an example of when you get rainfall that falls on a rock, and when that water stays there, it exchanges with CO2 that's in the atmosphere to form something called carbonic acid. Now, carbonic acid is very acidic and it will eat away at the rock slowly over time. So you can see here that all of these different places that water droplets were, and then the carbonic acid forms, and then it starts to be a self-perpetuating thing as it forms little divots and just eats away at it, so it catches more and more water. Another type of chemical weathering is something that you might be more familiar with, which is called oxidation, which is what rust is. So you get water on there, and then it starts this chemical reaction of oxidation. Now, not all minerals weather at the same rate, so it ends up, you get this thing called differential weathering. So differential weathering, can happen a lot of different ways, but there's one really cool example when you get buildings, old buildings that are made out of limestone that you see over here and sandstone. So what happens is over time, the limestone, which is more easily weathered, you can see it starts to break down and you get these kind of indentations, whereas the sandstone here is a little tougher and it ends up sticking around a little bit longer. So you get a process called differential weathering. Now that weathering process is the process of rocks breaking down into smaller and smaller pieces. So here in Missouri, we have a good example from Missouri red granite. Now granite is a type of rock that is made up of 3 separate and distinct minerals. Here in Missouri, we have this really distinctive Missouri red. So when you, perhaps you've noticed when you're driving around on the roads have a slightly red tint to them. Well, it's because this Missouri red granite, they use some of those remnants and it gets mixed into the roads and gives it that slightly reddish tint. Now that Missouri red granite can break down into primary minerals. So primary minerals are things like potassium feldspar, quartz, or biotite and hornblende. Now, when you look at the granite here, you can see how each of these shows up in there, but they're kind of mixed together in this rock. So you can see the reddish potassium-rich feldspars, which you can see here. You have the quartz, which is kind of clear, so it's a little harder to see. And then you have the darker biotite and hornblende that are kind of flecked throughout that. Now, feldspars are a really common primary mineral that end up making soil minerals or secondary minerals. So when that potassium feldspar starts to weather, you get clays, specifically a type of clay called kaolinite. And then it leaves over other things like potassium ions, right? It's a potassium feldspar, so you have lots of potassium left over. And then you also get silicon dioxide and other kind of weathering byproducts. So this weathering process from rocks to primary minerals to secondary minerals takes a really long time, and that is kind of the process that soils go through to weather. So secondary minerals, the most common type of secondary mineral in the world on Earth, are clays. So I know what you might be saying, this word clay, we keep using it to mean all different things, and you are not crazy. In fact, clay can refer to particle size. So that is the smallest size particle that we have, and it refers to particles that are less than 0.002 millimeters in diameter, or 2 microns. So it can refer to a particle size. It can also refer to a textural class. And specifically, it refers to the textural class that is rich in clay-sized particles. Makes sense? Hopefully, maybe a little confusing. But if that wasn't confusing enough, we also use the word clay to refer to a type of secondary mineral. So this type of mineral, secondary mineral, is referred to as phyllosilicate minerals. Now, that word phyllosilicate, you might not be familiar with it, so let's break it down real quick. So phyllo, or philo, comes from a Greek word for leaf, and it specifically refers to the stacking. So it's these very thin layers that then become stacked one on top of another. In Greece, they call phyllo dough, which is a type of dough they use to make sweet things like baklava, for example. And what it is it's very, very thin layers of dough that are stacked one on top of the other. And so that's how you can remember this phyllosilicate. Now, the other piece of this, silicate, refers to the fact that these clay minerals are rich in the element silica. So you put these together, it's stacks of silicate minerals. So you can, when we look at it under a very powerful microscope, you can start to see those stacks, right? You can see they're pretty thick stacks. And if you look here, you can see that, they have thin layers that are almost straight across that are one on top of the other, and it goes for a while. But remember, we're talking about weathering, and you can see also where that weathering starts to happen. You can see here that piece has broken off. You can also see pieces that are starting to peel away. So that weathering process, happens on these very small clay minerals. You can see it under a microscope. Now, if we were to zoom in even closer on these clay minerals, we could look at the mineral structure here. And there are a couple different types of clay mineral structures that we would find. So the first one I want to talk about is called a 2-to-1 clay. So we call it a 2-to-1 clay because there are 2 sheets within this sheet. So we have 2 tetrahedral sheets and an octahedral sheet. I like to think of 2-to-1 clays as like a little Oreo. So you see here is the cookie and you've got the cream filling here, right? So 2-to-1 clay is before anything has happened to that Oreo. Now, another type of clay is the 1-to-1 clays. So 1-to-1 clays have one of these tetrahedral sheets and one octahedral sheet. So this is like an Oreo after you do the twist off game, that you play when you're kids, and whoever the winner is the 1-to-1 clay here. So those clays can similarly weather, and that process is really important in soils. So we start off with those 2-to-1 clays, right? Again, 2-to-1, you have 2 tetrahedral sheets in your Oreo and 1 octahedral cream filling sheet here. Now, 2-to-1 clays can then break down into 1-to-1 clays. Again, we call it 1-to-1 because there's only 1 tetrahedral and 1 octahedral. So you can see that this tetrahedral is gone missing, right? And so we're down to a 1-to-1. That 1-to-1, you can lose the second tetrahedral sheet and you're just left with an octahedral sheet. So you can think of those as a 0-to-1, but really we usually refer to those as just iron and aluminum oxides. Now, one thing I want to kind of draw to your attention here is the relative amounts of things here. So tetrahedral sheets are silica rich and octahedral sheets are aluminum rich. So as things weather, you see that the proportion of silica relative to the amount of aluminum decreases, right? We have 2 silicon tetrahedral sheets, 1 aluminum octahedral sheet. So it's like a 2-to-1 ratio of silicon to aluminum. Then we have 1-to-1 silica to aluminum. And then eventually we're just left with lots of aluminum. So why does that matter? Well, if you remember back to last week's lecture, when we were talking about soil orders, our 2 most weathered soil orders, the ultisol and the oxisol, are usually relatively enriched in these aluminum oxides or iron oxides. And if you remember last week, I mentioned that that's what gives them their reddish color. Also in lab, you will see those reddish colors, and those are a good indicator that there's probably a lot of weathering happen. And it's because that red is finally able to shine through because we have a relatively high amount of iron and aluminum in these soils. Now, the 2-to-1s and the 1-to-1s, we generally refer to them as clay minerals. Those are secondary minerals and specifically clay minerals. And iron and aluminum oxides, we don't refer to them as clay minerals at all. We just refer to them as oxides. So you can see people using different terms, and I just think it's worthwhile to call that out just so you don't get confused. Now, when we look at these sheets here, the first one, as I mentioned, is a silica tetrahedral sheet. Now that silica is here and it's bound up with oxygen molecules, which are negatively charged. And they start to array themselves into this long chain of silicon and oxygen. And so then it forms this crystalline structure that is, again, these long, thin sheets. Similarly, we have this aluminum sheet, and the aluminum coordinates with both oxygen and hydroxyl groups to form these long crystalline structures. Now, sometimes these long crystalline structures, the cations here, the silica and the aluminum, can switch out with molecules that are in solution. Now, they'll only switch out with molecules that have a similar size to them. And you can see that, for example, aluminum will switch out with silica. And similarly, we can find magnesium in solution here, and that can switch out with aluminum. Now, one thing to note here is that these switch out with similar sizes only. It's hard to get something that's bigger than this molecule into that crystalline structure. So because they are similar size, similar morphology, and they're switching out with one another, we use the term isomorphous substitution. Now, when you get that isomorphous substitution, what usually happens is a molecule with a slightly less positive charge will switch out. So you can see here that silica is a 4+, aluminum is a 3+, and aluminum here is a 3+ and a 2+. So the net charge on this silica sheet or this aluminum sheet is actually slightly less once that isomorphous substitution happens. So when that substitution happens, the surface of these sheets ends up having a slightly negative charge. Now, with that slightly negative charge, you can get certain properties. Now, in soils, just as in real life, opposites attract. So this negatively charged surface can start to attract positively charged molecules in the soil solution. So you can get magnesium, and then that magnesium can actually be bumped off by another cation. They can substitute for one another on the surface there. So a calcium, for example, can bump off that magnesium. Similarly, on the edges of the clays, you can get other molecules also kind of exchanging with one another. Now, these are usually cations, these positively charged molecules, and because these cations are exchanging with one another, the ability of a soil to have that exchange happen, we refer to that as the cation exchange capacity, or CEC. Now, CEC is really important because a lot of these cations are actually nutrients. Magnesium, calcium, sodium, and potassium, for example, are all nutrients that plants need. So the CEC helps contribute to soil fertility or plant nutrient uptake. Now, not all of these cations are created equally. That is, some of them are more strongly attracted to the surface than others. And it happens in this kind of predictable fashion. So aluminum with the highest charge, that 3+, it has the highest charge density, is the most strongly absorbed. And then we can go down the lyotropic series, it's called here, down to sodium, which is the least strongly attracted because it has a big radius and a low charge. Now, I want to take a second here and just focus on this one specific part of it, the H+. Now, I want to focus on that because hydrogen is what contributes to pH. Now, you'll remember back to chemistry, hydrogen is inversely related to pH. So if you have more hydrogen, if hydrogen is higher, you have a low pH, and low pH is related to acidity. So a low pH means that this soil would be acidic. Now what happens is when you have an acidic soil, then a lot of that cation exchange capacity can be taken up by hydrogen ions. And those hydrogen ions can get absorbed pretty closely there, right? Remember, hydrogen was one of the most strongly absorbed to the CEC. But what that means is that soils can start to absorb negatively charged molecules too. So those are anions. So we can get things like phosphate or chloride, anions to absorb onto that soil that is acidic. Now, because that doesn't happen all the time and it only happens when we're at a low pH, we call that pH-dependent charge, okay? So, but pH-dependent charge is not the only time that negatively charged molecules can absorb onto soils, these anions. There's also such a thing as anion exchange capacity. Now, this is much less common than cation exchange capacity, but it does happen, and you can get similarly other things that are absorbing onto the positively charged regions of soils. Now, although both of these can result in the same thing, which is these anions absorbing to soil, they're really different from one another. Now, for a couple reasons, I want to draw this out. First off, pH-dependent charge is a combination of two things. So it's a combination of what's going on in solution, remember that pH, and it's also a combination of that with that surface charge, which is a structural occurrence from isomorphous substitution, remember? Now, whereas anion exchange capacity is purely a surface charge thing or a structural thing that happens from that crystalline structure. So these two are very different from one another in soils, even if the effect can look the same sometimes. So not all clays have a similar exchange capacity, right? Now remember, we have 2-to-1 clays that weather into 1-to-1s, which can weather into iron and aluminum oxides. Now, the 2-to-1 clays are more likely to have high cation exchange capacity, whereas iron and aluminum oxides have more of this pH-dependent charge and anion exchange capacity, right? So this is a little bit a function of that weathering from 2-to-1s to 1-to-1s to oxides. Now, just to give you some examples here to show you how that happens, let's start over here with the 2-to-1 clays. So there are lots of different types of 2-to-1 clays. So a couple examples here are vermiculite and montmorillonite. So vermiculite has a negative 125 milliequivalents per 100 grams of cation exchange capacity. Remember, we have negative charge here, which negative exchange capacity, and because it's negatively charged, it attracts cations, the positively charged things. Similarly, montmorillonite has slightly less negative charge, but it still has lots of cation exchange capacity. Then when we look at 1-to-1 clays, for example, kaolinite is the most common 1-to-1 clay, you see that it still has negative charge, but it's slightly less negative charge than the 2-to-1 clays. Well, actually, it's a lot more negative or a lot less negative charge, right? It's about an order of magnitude or so. But you can see that it still has that negative charge, that negative charge then attracts that cations, right? Those nutrients. However, when we go over to these iron and aluminum oxides, you see that they start to become positively charged, right? So we have gibbsite here, which is a aluminum oxide, and we have goethite, which is an iron oxide. Now, note that these are positively charged, so opposites attract. These positively charged exchange capacities can attract those anions. Now, remember in lab, we did the calculation for these milliequivalents per 100 grams, but those aren't the only units that you can see exchange capacity in. Another common one that you'll see is centimoles of charge per kilogram of soil. And we have a 1-to-1 relationship between milliequivalents per 100 grams and centimoles per kilogram of soil. So that's all for right now, but I want to review real quick. So first off, there are 2 types of weathering. Physical weathering, which is what breaks apart the rocks physically, it rips it apart, right? And then there's also chemical weathering, which changes the chemical composition and dissolves the rocks. Now, those rocks are degrade into primary minerals, and which then further break down into secondary minerals. And clays are the most common type of secondary minerals. Now, these clay minerals have silica-rich crystalline sheets. Those silica-rich crystalline sheets are tetrahedral sheets, and they are tightly stacked one on top of the other, which is why they're called phyllosilicates. They are phyllo, so they're stacked like phyllo dough, and they are silicates, so they are silicon-rich. Now, those phyllosilicates can have a process called isomorphous substitution. So that is substitution of molecules of similar size. And that isomorphous substitution leads to negatively charged clay particles. Those negatively charged clay particles let cations bind to them. The positively charged molecules can bind to the CEC, and that CEC is a way of thinking about nutrient retention in soils. Acidic soils can become positively charged because all of the CEC is taken up by hydrogen plus ions. We call that pH-dependent charge. So in acidic soils, soils can start to bind anions. And in general, we see that 2-to-1 clays have higher CEC than 1-to-1 clays. And therefore 2-to-1 clays are generally considered more fertile soils. So that's it for right now. And I look forward to seeing you all in class this week.